In the previous segment, we derived this expression which related Young's modulus, Poisson's ratio and the shear modulus. But we promised that in this segment we will see another perspective of deriving the same thing. Okay. So, let us try to see what that perspective is and again derive the same expression. For this, we start with a cubic body. Okay. Suppose this is of side length say L. So, area is L squared. So, this is also L. Okay. And now we apply forces like this on this side, tensile force of, sorry, I will draw like this maybe, yeah, P, the tensile force on this x, maybe this is x direction, so x direction, and a compressive force of the same magnitude P. Okay. Now, if this body is under such a loading condition, what would be the change in length over length or the strain in this direction? Say I'll say delta L over L will be nothing but P over A, if A is the area, that is L squared, over E, right. So, that is because of this elongation, but along with that, see, there is a compressive force in this direction, and because of which there will be an elongation due to the Poisson's effect. Okay. So, now that will come to be plus nu times again P over AE, right, because the direct stress or strain will be P over AE in the y direction multiplied by nu. So, that x direction is lateral for this, so that will be the condition. So, which implies that your delta L over L will be equal to 1 plus nu times P over AE. Okay. Yeah, or in fact, I would like to, sorry, I would write it in a slightly different form. Say 1 plus nu, just for sake of style, nothing else, like this, times P over A, because this kind of an expression we will get somewhere else and we will match them. Okay. So, now please keep this thing, this result in mind, keep it aside. So, this is the change in length in the tensile direction, because in the compressive direction the same magnitude, but it will be just negative, so that it will be compressed. Okay. Magnitude wise it will be the same, and this is the elongation or the strain in the x direction, in the tensile direction, which is this when P and P are to be kept in mind. Okay. Now, what we will do, we will take the same cube. The same cube is there with us, and now we are applying the loading like this now, shear stresses Q, Q, Q and Q. Okay. Whenever we have, suppose we want to apply this shear, our main idea is to apply this Q, but obviously this stresses will be there. Okay. So, to maintain the equilibrium. So, stresses definitely will be in this form that we now know. Now, if this is the state of stress of that tube or applied loading conditions, now let us see what happens to, let me first draw the diagonals. So, this diagonal I will call say B, and I will draw another diagonal, say this one I will call A. Okay. So, these are the diagonals of the cube, say length of D. So, diagonal length is D, which is nothing but L under root 2, right, length of the diagonals. Anyways, so now just try to see that if I consider this portion, or if I try to see what sort of stress is existing on this diagonal A, right. So, what will be the situation? See, we are having this is the kind of block on which we are looking the forces for, and now we are looking for these forces, the stresses, and let me draw even the Q's here. So, the Q was acting like this. So, now this angle and this angle all are 45 degrees. Okay. Now, in this direction it is Q over root 2, and similarly for this Q which was acting here, this Q, I'll again have this and this. So, Q over root 2 and Q over root 2. Now, this also Q over root 2, right. Now, these parallel forces parallel to the surface A, if I the diagonal A, okay. So, this is I am concerned with the diagonal A. So, the forces which are parallel to it, they cancel each other, but the forces which are normal to that, they add up to give me a total force of, or I'll say that normal stress in this particular direction, I'll normal to A, okay, sigma in that direction, and it's tensile. So, that is very important. Okay, tensile normal stress in this direction is equal to root 2 times Q, because Q over root 2 plus Q over root 2. So, root 2 Q, but what is the area under which or on which it is acting? That is this A, area of the whole thing, times root 2. So, root 2 times this A I am using for many things, so it's actually confusing. So, what I would do is A prime is the area, okay, so that there is no confusion with the diagonal which I have named later on to be A. So, yeah, fine, that is fine. So, now this will be root 2 times A primed, right, which is nothing but again Q over A primed. And the same argument if you do for this diagonal, the diagonal B, then again you will get a compressive, okay, load of sigma again perpendicular to B, this time will be equal to Q over sorry, A prime. A prime is the area, fine. So this is the compressive load which comes onto on this side. So that means what we can interpret this result as like this. You have let me draw, say, the green square like that, and if I now draw 45-degree lines like that, okay, so like that. It doesn't look like a square. So basically, yeah, you know, okay, so it's a square, you now know that, okay. So, so now on this square here, you are having a root 2q force is acting, tensile. On this you have compressive root 2q, and the areas of these are by default root 2 times a, like that, root 2 times a, if the area here is a. So that means the conclusion of up to this point is, when you have, you know, stresses like this, Q, Q, Q and Q, and if you consider 45-degree rotated areas, you will get a stress field which looks like this one, which is tensile in the other side and compressive on this side, and whose stress is again Q over A, right? So that means, see here, the area is again Q over A, tensile, and Q over A, compressive. So this you can see in this way, or another way to look at this is, say, you can consider an area or square segment like this. Anything is fine, because again, anytime you think of this, it has to be shrunk to a point, and then so specific sizes doesn't matter, okay. So they don't matter, so you can think that, okay, on this also I'll just draw once, it will be again the same stress. Okay. So that means if we apply equal amount of compression and tension on two perpendicular direction, it is equivalent to seeing a pure shear stress field at a 45-degree rotated configuration, and vice versa. So that is a thing which should be kept in mind, and then we will proceed to the next step of argument. Okay. Now then, now here, if this was our original, so this green was our original, what do I call the square, it means this length was what? This was d, right? If you see this, yeah, so this was d. Now if under these kind of loading, what would be the value of delta d over d? This we can now directly write from the first argument which we had done. Under such a loading condition, you have delta L by L is this. Okay. So that means here we will have 1 plus nu over E times Q over A. Right? Because root 2 Q and over root 2 A I should have written, but the root 2 cancels out, and this. Okay. Now this is one relationship we got, that under this shearing stresses, the change in diagonal over diagonal, that is the strain in the diagonal, happens to be this. Now let us see this deformation, a slightly closer view of that by say drawing this. Say initially, suppose this was our square section, and once it is, we have applied the shear, it has gone to something like this. Okay. And now this is our gamma, the shearing strain. Okay. Now suppose this length is say delta, so your gamma is nothing but, everything is small, so again tan theta is theta, which is nothing but delta over L, because these lengths are L. So if you remember, so this was L. Okay. So delta over L is this gamma, but then okay, let me draw. So this was my diagonal, right? And now the changed diagonal is this one. Okay. Now what is the change in, this is the changed diagonal. So what is the change in diagonal? If I draw a perpendicular here, okay, so everything again small, so that means this much, this length is my delta D. Okay. If that is delta D, then this angle is 45 degrees. So delta, your delta is nothing but delta D times root 2. Okay. So that means here I can just substitute that root 2 delta D over L, but then L is what? D over root 2. So I'll put D over root 2, which is nothing but you will get 2 times delta D over D. But then now you remember this term, we just derived it here. It is, yeah, I'll write it here. So this will be equal to 2 times 1 plus nu over E times Q over A, right? Yeah, so then what is this? Gamma, which is nothing but, so I can just now write that my shear stress over G is equal to 2 times 1 plus nu over E times, that is nothing but my shear stress again. So they cancel out, and again we are left with, or here only I'll write, your G is nothing but E over 2 times 1 plus nu. Sorry, I'll write it there, plus nu. Okay. So it again we arrived at the same relationship, which we definitely should get the same expression we were looking for, but the arguments, the concepts which are used here are very different, means at least to on the first look they look very different, and this concept of equivalence of a tensile plus compressive is equivalent to a pure shear at 45 degree. That is a very important thing which will come up again and again in many problems when you solve, and that has been used now to derive the same expression. So please go through this again and make sure that you understand both the ways of deriving this relationship between E, G and nu. And yeah, so we are finally, I'll write it here. So we have G is equal to E over 2 times 1 plus nu. So now if you put nu, its smallest value is 0, so you get what? G will be E over 2, and if you put 0.5 here, you will get E over 3. So G will lie between them. Okay, so your shear modulus will lie between E over 3 to E over 2. So these are two of the things which you should always keep in mind, and both the ways of interpretation of the derivation of the relationship. So see you in the next segment with some other topics. Bye bye.